In this lecture, we're going to finish off our section on integration. Now, we've been working our way through these topics, and today we're going to look at so-called rationalizing substitutions and Weierstrass substitutions. Okay, so let's just get straight into it and do an example. Here is an integral whose integrand here is not a rational function. It's not a rational function. Okay, so we cannot use the techniques that we've been doing, like partial fractions, to solve this problem straight out. But the question is, can we make it a rational, the integral of a rational function? What do you reckon? Yes, we can. Now, the thing that gets in the way here is this power of 1/4. Okay, if that power was an integer, 1, 2, 3, then we could, it is a rational function, and we could apply our techniques. So can anyone suggest a suitable substitution to make this a rational, the integral of a rational function? Say again? Oh, yes. The suggestion is x equals u to the power of 4. Well, that's what we're going to do. Actually, I'm going to switch it around a little bit and let u equal x to the 1/4. So if you rearrange that, you get x equals u to the power 4. Now, with substitutions, you of course need the differential. We need to calculate dx in terms of du. So we can do that from this expression. It's going to be 4u cubed du. So now I can take those pieces and substitute them in, and hopefully we'll get something that we can compute. All right, so replace dx with this. And the bottom is going to be replaced with 1 plus u. Is that a rational, the integral of a rational function? Yes, it is. But if you look at the numerator, you've got a u cubed up top. The highest power down the bottom is power 1. So what we're going to have to do is split that up somehow. Okay, now you could use long division, but can anyone see a better way? Yes. Even simpler than that. Yeah. Just play with the numerator. Put a +1 up the top. Well, actually a +4 up the top and a -4 up the top. Okay, take out the factor of 4 and you can cancel. So I'm going to take out that factor of 4. I'm going to add 1 and take 1 away. So there I've got u cubed plus 1. I can factorise that and get the following. Bless you. Okay, so now I can split that up and cancel. So now I can just integrate each of those terms, right? So let's do that. Now I'm just going to put the plus c out on the right-hand side. So I've done my integration. All I need to do now is get back to x's. So I can just back substitute, right? U is x to the 1/4, so I can just replace u with x to the 1/4 down here. Oh, sorry, x. So 1/2 times x to the 1/2. Done. Okay, nothing fancy. It would be hard though if you couldn't get that initial substitution. It would be very difficult. All right, questions? Right, so that's a good technique. In general, it'll work. There may be other techniques to solve that problem, but I feel this is a fairly good one. Okay, so that's one substitution that can get you to that's one technique that can get you to the integral of a rational function. Let's look at another one. All right, here we're asked to integrate the following expression. Similar principles can be applied here. We need to come up with some substitution to make this, the integrand, the thing we're integrating, a rational function. Any suggestions? U equals e to the x. Who said that? Okay, you're on fire today. Who? Where did that come from? I'm confused. Where did you pull that from, man? What? Yeah, it does. It does. But even I want simple stuff, man. E to the 2x. What's that? That's e to the x, right? Times e to the x, which is e to the x all squared. So maybe, just maybe, I can somehow turn that e to the 2x into something squared. Oh, yeah. That's the answer I was looking for. Your answer is very valid too, though. All right, so let u equal e to the x. So let's calculate the differentials. What we would like to do is get that differential du in terms of I guess u, right? So you actually want to substitute this dx out. So you want to get dx in terms of du and u. So I can just substitute in here. So what's dx going to be? It's going to be 1 on u du. Okay, so we take those two bits, u and dx, and substitute in. All right, so we're going to get this for dx, and this is going to be u squared minus 1. All right. So now what? Anyone? No, you've said enough. You're on fire. Let someone else have a go. Anyone? Up the back, the corporate box. Anyone? Come on. Oh, good attempt. Almost. U equals sec theta, because we've got a u squared minus 1. Okay? So this now involves a trig substitution, right? So if u equals sec theta, what's du going to be? Sec theta tan theta d theta. All right, so let's substitute in and see what we get. So now I can cancel off. I can replace sec squared minus 1 with tan squared, and I'll get the following. Now I don't need to worry about absolute values here, because I guess implicitly in this substitution I'm only considering theta strictly between 0 and pi on 2, okay? Okay, so that's pretty easy integration. Theta plus a constant. So now what we need to do is get back to our original x's. Okay, so first let's go back to the u's. If u equals sec theta, then theta is going to be sec inverse u. And then we've got to go back again. U is just e to the x. Okay, so that's a difficult problem. It involves two substitutions. Okay? Where does that sit on the scale of what you might get? It's probably no. It's above what you'd see in a class test, because it's too involved for 20 minutes, right? Like, well, one question out of 4 in 20. You may get something like that in the end exam. Yes. Yep. You could, yes, you could. That's an excellent question. The question is, why not use a different substitution? Yes, you can absolutely do that. Okay, the substitutions that I'm solving these problems with are not necessarily unique. So I could use one substitution, you could use a different substitution, and we could both come up with the same answer. Okay? Yes, excellent. Good question. Any other questions?
Yes. Why not just let e to power x equals to
Yeah, right. You could do that as well. Okay? So I'm trying to give you the simplest, most, well, it's not the shortest solution, but hopefully it's the one that makes the most sense. You can use other substitutions. Absolutely. Oh, yes. 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 It should be. That's a good question too. Okay. In a previous lecture, we met Oliver Heaviside. Let me introduce you to the work of a German mathematician called Carl Weierstrass. Now, Carl Weierstrass is famous for many, many things. Okay, for example, continuity. He was the guy that actually nailed down the definition of continuity. So you can thank him for that. He's also famous for a so-called T substitution, which I've underlined. Okay? No, it's not the T substitution. It's the Weierstrass substitution. Okay? Now, who was Weierstrass? I'm glad you asked. Weierstrass went to university in Germany, and his dad wanted him to be a banker. A banker. All right? Wanted to go into finance and make lots of money. But Carl was having none of it. So he just studied, he refused to go to any lectures. He just studied maths in his own time, and he used to drink a lot and get into fights. He also did a lot of fencing, you know, with swords and stuff. So anyway, after 4 years, he returned home without a degree. But you know, he didn't care. He was doing what he liked. Okay, maybe some of you feel the pressure that your parents put on you. Anyway, Weierstrass was a bit of a rebel. Anyway, he made some of the most wonderful advancements in maths. So this is one of them. Okay, so what's this useful for? The Weierstrass substitution is useful for integrals involving a rational expression in sine and or cos. So let me just show you what that, something like that. Okay, that's a tough integral. Now, this little magic substitution, under that substitution, you can come up with expressions for sine x, cos x, and the differentials in this form. And I've given you some justification down here. Don't worry too much about that. But let me show you how it works in practice. Before we get to that, though, why would you want to integrate something like this? Why? Okay, what? Who said because you told me to? No, that's not right. Okay? I mean, that is a strange-looking integral. So what I'm going to do before I solve it is actually give you, it's a rather confected example, but you know, my heart's in the right place. Okay. All right, this is another very common problem in physics, in applied science and engineering, where you're given an object and you want to calculate the mass, and you know the density of the object, right, at each point. In this example, we've got a thin plate in the xy plane that occupies this kind of discular region. Now, I've changed these, so I think your notes has got a pi on 4 here, so you might just want to adjust that. So here's a rough sketch of the region that this plate occupies in the plane. Now, at any point in that plane, you've got a density associated with the point. Okay, here, and this again, this is a fairly confected example. It's given by this function. So basically, as you move away from the origin, the density decreases. Okay, so to calculate the total mass of the plate, essentially you integrate the density over this two-dimensional region. Now, don't worry too much about these double integral signs. Just think of them as one integral inside another. You do the inside integral first, and then you do the outside integral. Now, that's a tough integral. That's a tough integral. Okay, so as I've shown you in other examples, we make a substitution to reduce this to a simpler problem. Now, if you do that, you actually get down to this example. So you can think of integrating these two things separately and multiplying them together. All right? Again, a slightly confected example, but one of the places where integrals of cosine and sine pop up is when you switch to polar coordinates and you need to do something. Okay? Very, very important. Very important. All right, so let's do the example and see how it works. I'm going to show you one that I've prepared earlier first. Here we're asked to show that I defined by this integral is pi divided by root 3 on 3. So let's just step through it. We make the Weierstrass substitution. And then we can write cos x in terms of t, and also calculate the differentials. Then you just substitute in for cos x up here and dx up here, and you get some nice cancellation. We get the integral of this function here, which can be integrated at once. Okay, that's pretty good. Pretty good. All right, so let's do this problem here. So we're going to let t equal tan x on 2. So using these expressions here, we're just going to substitute in for dx, cos x, and sin x. So we're going to get a lot of t's. Okay, so So we've got a big mess. All we need to do is simplify and then perform the integration. So if we simplify here, we can actually cancel off the 1 plus t squareds. Okay, you actually get a common factor of 2 in the top and the bottom, and you can cancel that off, and it's reduced to this. So back substituting, we end up with this. That's a hard integral. Anyone seen anything like that before? That t substitution? A couple of people. At the back? You guys seen it? Yes? Yes? At school? Yeah. Did you know it was Weierstrass? No, you just called the t substitution, right? We've got to give Weierstrass his dues, you know? All right, questions. Would you get something like that in a class test? No way. If you get something like that, you come to me. All right? Storm out of there and go, nah, this isn't on. Okay? This is even, I would say that this is even beyond the end of semester test as well. Okay? All right. I'm going to stop here. Tomorrow is an important lecture. We now finish section 2. Okay? So I'll see you all tomorrow.